Thank you very much. There are two names on the slide. I'd like to acknowledge the contribution of my colleague Cecile, who's helped put this presentation together. However, many more people have been involved in the background. And in Workstreet 1, there have been a range of people with expertise as growers, as scientists, and as life cycle analysts. And without their contribution, the model wouldn't have got to where it is. So Palm GHG is the name of the tool that we've developed. Why do we need it? All agriculture produces greenhouse gases. And the scientific consensus, as we know, is that additional greenhouse gases are damaging to the climate. In other words, they're a form of pollution. And as responsible growers, we're responsible for managing pollution. And in order to manage, we have to measure. The tool essentially is a balance. You measure the emissions, and you set that against the sequestration, and you end up with a balance. We can't measure directly, so we have to estimate. The tool quantifies the major forms of the emissions and sequestration from the mill being the accounting unit, and its supply base, which is the estate and the outgrowers. The tool has been developed so that it is harmonized with international standards, methodologies, and the content of the calculator and the features have been discussed extensively, should I say exhaustively, within the whole working group. I don't know if you can read all that. It's the system boundaries. Previous published work has shown that 7 sources can account for the majority of your emissions, over 95%. And so these are the land clearing, which is by the dominant contribution of emissions. It may be oil palm if you're doing a replant. It may be another form of land use. It could be logged forest, agricultural crops, or grassland. Then the next, in the field, we have use of fertilizer. The manufacturing and transport of fertilizer contributes emissions. And then the use of your fertilizer, the nitrogen fertilizer, results in nitrous oxide. Nitrous oxide is a very potent greenhouse gas, nearly 300 times more potent than CO2. So it's important to include the nitrous oxide, both from the fertilizers, but also from your crop residues. And there is provision for measuring the nitrous oxide resulting from use of EFB and POEM. The other field use is fossil fuel. You use fuel dominantly for transporting your crop, but there are many other activities, whether it's land clearing or building roads, whatever. There's a lot of fossil fuel used, and that all has to be accounted for. The final component of the field is peat, and you'll be hearing more about peat later, but it's potentially a large source of CO2. And then you come to the mill, and there are 2 sources of emissions. There's the methane, which is produced when you digest your POEM in your anaerobic ponds. And then there's a bit of fuel used in the mill for startup, etc. And all these are all the emissions. And the emissions are set against sequestration. And the main sequestration, of course, is in the palms. The palms are growing over a 25-year cycle, and each year it is sequestering more CO2. And then also there's a potential credit. If the mill is self-sufficient in, or has a surplus of fuel, you can export power. And if you're capturing your POEM and generating electricity, you're exporting electricity outside your system boundary, you get a credit because you're saving fossil fuel being produced elsewhere. And then this, the actual model is a spreadsheet, and it accounts for all the emissions, the sequestration, produces the net emissions, and then these are allocated to your crop products. So we work it all out for the estate and the outgrowers on an area basis, allocate it to the FFB, and then this is subsequently allocated to your CPO, your crude palm oil, and the kernel on a mass basis, and then subsequently could be further allocated to subsequent co-products, whether it be refined products or if you're producing biodiesel, and then you have different allocation procedures. It has to be done on the basis of energy rather than mass. The main features of the model are that it's quite adaptive. You can account for different rotation lengths, different oil palm growth data. We provide default data, but default data does for the oil palm growth data, but anything else where there's a default, if the user feels that he has better data, then of course he can use it, but he also has to justify it. And there's procedures for doing that. It allows for the calculation of the greenhouse gases per, as I explained, for the CPO, for your palm kernel, for the biodiesel, and compatible with the directive in Europe. It allows for CO2 emissions from the land use change and from the peat. I've already explained it allocates the emissions between different products. You can do it as a one-off, as just to see what your situation is, or if you wish, you can do it on an annual basis to monitor your change. And also, quite powerfully, it allows for scenario testing, and I'll be demonstrating that in a minute. So, having developed the model, we decided to test it, and we had a pilot testing phase this year. 9 companies took part, and the objective was to see how they found it, how user-friendly it was, whether the data that we required was available, and also to get